Hello everyone, and thank you for attending today's webinar, Bridging the CDN Capacity Gap with near 400 Gigabits Video Delivery, sponsored by Varnish Software with participation from Intel. Before we begin, I want to cover a few housekeeping items. On the left-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit them to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Towards the end of today's presentation, please complete the survey that is open on your screen. The survey will only take 1 minute to complete, and your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn over the event to Heavy Readings Principal Analyst Jennifer Clark. Jennifer?
Thank you very much, Catherine, and welcome everyone to today's webinar, Bridging the CDN Capacity Gap with near 400 gigabit per second video delivery. In it, I am going to be opening up today's webinar with some information from Heavy Reading and Omdia research that describes what we are seeing in the market. And then I'm going to hand it over to Nash Kleppen from Intel. And Nash, you want to say hi?
Hi, I'm Nash at Intel. I have been working on distributed storage at Intel for the last 7 years. And more recently, I've been working on content delivery networks.
Excellent. Thank you, Nash. We'll then be handing it over to Paul Johansson from Varnish Software. Paul?
Hello, my name is Paul. I work as a senior developer and project manager. I've also gotten the fancy title of Director of Core Development quite recently. And I've been working with high-speed HTTP caching since 2016.
Excellent. Thank you, Paul. And then we will be hearing from Asad Ahmed from Varnish Software. Asad?
Hey, my name is Asad, and I've been working for Varnish for close to 1 year. And before joining Varnish, I did my master thesis in optimizing TCP for low round trip.
Excellent. So we have a great set of speakers that are going to be talking to us at today's webinar, but let me begin with a little bit of information about what we are seeing in the network. First, we all know video is eclipsing all network traffic. You'll see those 3 largest magenta, purple, cyan bars represent ad-based video, over-the-top video subscriptions, and social video. Video traffic has really taken the place of our commute, hasn't it? It's taken the place of air traffic. The pandemic has accelerated the widespread adoption of video conferencing platforms, but the genie is not going to be going back in the bottle as those restrictions brought on by the pandemic loosen up. We're going to continue to see video dominating the network for the foreseeable future. And in addition to just video sessions, each video session itself is going to be putting more traffic onto the network as you transition from standard definition video to high def to ultra high def or 4K video. And keep in mind that this exhibit you see here is households. It's not traffic. The UHD impact on traffic and connectivity demands is dramatic. For standard def SD streaming, you need a minimum about 3 to 5 megabits of connectivity. For high def, you're going to need 5 to 8. For 4K UHD, you're going to need a minimum of 25 megabits, but connections of 50 megabits really are recommended to cover all the scenarios, particularly streaming live events. So as a result of this impact of video on the network itself, we are seeing a nice accelerated growth in the CDN market. With that growth in video traffic comes an equally positive growth in the CDN market as carriers work to strike a balance in terms of where they place content far enough down into the network to conserve the network resources and improve customer experience. Carriers are looking for a robust CDN solution that can react to these shifting sands of content, moving with agility as pockets or waves of demand move through the network. As a result, the CDNs have become stronger, both financially and functionally, through this pandemic. And these positive market prospects are seeing the CDNs focusing on, yes, regional expansion, market share improvement, but also very much on technological development. Live streaming has been growing significantly, and COVID-19 has accelerated the trend. In the new normal environment, people are hungrier than ever for entertainment via live events such as sports, concerts, theater. Streaming has become the main way of delivering those events. Offering a premium experience for users and increasing monetization for content providers has been the industry's aim in 2021. We're seeing service providers looking to increase the monetization of live streaming, as you see here, by enhancing viewing experience with new features, resulting in higher user engagement. And as you see here on the last bullet, anything that impacts that experience can ruin even the richest streaming experience. So we're looking to minimize latency. We're looking to minimize any jitter that's involved in that stream as well. So with that quick overview of some of the trends that we see in the market overall, let me hand it over to Nash. Nash?
All right. So in addition to the market forces that Jennifer just covered, I'm going to talk a little bit more about some of the technological things at play. And then I will discuss CDN system design and how to design for high performance NUMA-optimized systems. Paul will discuss Varnish, its features and its capabilities. Assad will discuss the new NUMA awareness features in Varnish. And then I will come back to get into some of the hardware details and then the benchmarking results that we have for you today. So in addition to what Jennifer just covered, there's some technological shifts going on as well. Recently, 100 gigabit Ethernet has become more available, and the supporting equipment for it, such as switches, has become less expensive. This enables on the individual server level to increase the throughput of the entire system. When you start installing multiples of those, say 200 gig links or 400 gig links in a system, the efficiency of the software and the performance capability of the hardware as it is installed in that server is much more important than it used to be. And so with this collaboration between Varnish and Intel, we've been working on both software and hardware improvements to improve the overall performance of the server, and as a result of increasing the performance on that server, improve the performance per watt or performance per TCO. And as previously mentioned, this work has included the NUMA optimizations, as well as some hardware configurations. So let's get into CDN system design as it pertains to NUMA. So with these networking changes, there are also storage changes. NVMe is now broadly available in most of the servers that are on the market. PCI Express Gen 4 has increased the throughput of both the I/O for networking and the I/O for those storage devices. Traditionally, on servers, we've scaled up performance by adding a second socket when one socket is not able to meet the load requirements. With a dual socket machine, we now have a NUMA architecture, a non-uniform memory access. This means that the system is aware that there are two separate sockets in the machine and that they have different distances to resources than the local resources, such as an I/O device or memory. On an Intel system, the link between those two sockets is UPI. In general, what we've observed with these systems is that there's enough bandwidth on the UPI, but traversing NUMA domains, so going from socket 0 to socket 1, adds latency. And you can improve that latency by making the accesses more local. That latency impact is, again, most pronounced when you are running at very high performance. If you had only, say, a 10 gigabit link, you may not notice. When you start to have multiple 100 gigabit per second links, it becomes very apparent. We're going to talk about some specific hardware configurations, and these configurations are somewhat optimized for this type of application. Rather than a typical OEM system that is targeting a very general purpose use case, and as a result makes some design choices that tends to favor the possibility of having a depopulated single socket design as well as a fully populated dual socket design. So if we look at NUMA as it pertains to an Intel system, a dual socket Intel system on the slide here, what we see is we have these two sockets. Socket 0 is a NUMA node and socket 1 is a NUMA node. And each of them will have some amount of networking and some amount of storage. What we see here in the orange line and the green line is that there are different distances from any given core to any given I/O resource or memory resource. So socket 0, if it goes to memory that is attached to socket 1, must traverse UPI, must incur that latency to get to that resource. One important distinction I'd like to make here is that a NUMA zone and a socket are not equivalent. Depending upon the exact architecture of the hardware and the exact system configuration, there are frequently more than one NUMA node per socket. You could have 1, 2, 4, 8, or up to 16 NUMA nodes in modern hardware. And so if we start to look at how this impacts things, if we take a case where we have the compute occurring on one socket and the I/O resources available on the second socket, we can see that as the data comes in off the NIC, it has to traverse UPI. Some compute will occur. Then we need to go retrieve that data from the disk. It traverses UPI again. And then now that we've computed it again and fully formed our response to this request, we have to send it across UPI a third time to get out to the NIC. And as you can see in the table here, there's a significant impact, not just in throughput, but in latency. If we look at a different case where we have only the disks are remote, the NICs and the memory are local, we see that we also have a significant performance impact here. Again, in both latency and in throughput. And so this is the importance of NUMA locality as it pertains to both throughput and latency performance with these types of systems. So a typical dual socket system, as I mentioned, is designed for a general case. And in this general case, it is typically a compute-bound workload rather than an I/O-bound workload. And so I/O is not the highest priority in the design. As a result, it's pretty common to see an imbalance between socket 0 and socket 1 on the amount of I/O that can be installed and the types of I/O that can be installed. In the example that I'm showing here, this is a fairly good general purpose design where you can get 4 drives on socket 0 as well as a NIC and 6 drives on socket 1 as well as a NIC. Some systems are worse, some systems are better. For those interested in the details of how we made those experiments on the NUMA locality and its impact, here are the details. But now I'm going to hand it off to Paul to talk about Varnish and some of its features and capabilities. Paul?
Thank you, Nash. Let's go to the next slide here. Can't find the button. There it is. Yeah. So Varnish is, as you might have realized already, HTTP cache. This is a very simplified figure diagram. At the top, you have the clients, which are cell phones, computers, even set-top boxes, and actually whatever needs to fetch stuff over HTTP. you have at the top, and then you have Varnish running on a server in the middle, and finally there are origins at the bottom. These are conventional web servers that run the web server software. And the obvious question is, why do you put this thing in the middle? And we already touched upon some of these things. For example, you have the option of putting these caches close to the different clients. If you're distributing video, you can have caches around the world and have origin servers nearby your main data center. And of course, you will run Varnish on hardware which is fit for the purpose, while the origin servers will run on whatever makes sense for their use cases. Here you can see that there are three requests from the clients to, or 3 arrows from the clients to Varnish and 2 to the origin. But what we are talking about here today is use cases where you have a very big cache in the middle and you get very high bit rate. So you lessen the load on the origin service, and you can get away with much less resource usage there, in addition to the network resource savings you gain from having the Varnish server close to the clients. So I would like to say a few words about what Varnish can do. And of course, we have the Varnish Enterprise solution, and it has some features which are common to the open source version, and we have many enterprise versions. So first of all, Varnish is a cache with stream and request coalescing, which means that if you have 2 clients coming in at the same time, and it's a cache miss, you will only get a single request to the backend. And when the data comes back from the backend, both of the clients will receive that data in a streaming manner. That means that the cache is reading from the origin and writing to all of the clients requesting that resource at the same time. This is typically not something you'd like to implement in an origin server. You have something called VCL, the Varnish Configuration Language, and it's used to make custom behavior inside of the cache. And typically, when you get a response from the origin, you will either respect the RFC, trust that the origin server knows how to instruct the cache, how to cache things, but you can override this, and that's depressingly common, that you need to fix whatever behavior the origin will describe. You can also do routing, which means that you can consider the request and choose whatever origin server which is best for that, correct for that request. And you can do business logic as well. You can change the request as it comes in. You can apply application, so a web application firewall inside of the cache. And you can even implement paywalls, so which means that you can cache both the pay for and the you need to pay for this. You need to have this subscription to see this page, and so on. We have one of our main enterprise features is that we have both memory and storage, persistent storage cache solutions, and that's what Nash is going to talk about later when you're doing the benchmarks. And finally, we have high performance architecture, and that's an interesting one. You never know how well this architecture will stand the test of time. And I'll just talk a bit of that on the next slide here. So why is it fast? The first one is that it works well with the architecture, which is evolved from years behind. 15 years ago when the Varnish project started, it turns out that the architecture that was chosen at that point actually works well with the modern hardware. We have a threading model where you have very few context switches. We have worker threads, and they do as much work as they can before handing over the letting the kernel know what to do, which bytes to send where, and we minimize memory copies. As you saw in Nash's slide, you had the UPI bus being traversed when you had memory access in the wrong NUMA node, and we tried to reduce the number of memory copies and memory accesses resulting from this. Lock contention is also very important to avoid when doing working with systems with high core counts. And finally, we use APIs which are modern. In particular, we use asynchronous direct I/O, and we try to always follow the new stuff, which makes things faster. And one of them is, of course, NUMA support. And I'm handing over to Assad, who will talk about this now.
Yeah, thanks. So when working with a dual shot system, we found that Varnish was not running perfect as we were used to, and we identified the bottleneck to be the UPI bus using the process counter monitor tool, open source tool by Intel. And as you can see on the left, we had problems with memory access taking place on the remote node almost 1/3 of the time, which contributed in adding latency as this memory access went over the UPI bus. Thus, the majority of the time was spent by Varnish not doing useful work on this dual circuit system, but rather waiting for those copies or the memory access. On the right-hand side, we see what happens when Varnish is made NUMA-aware, and the memory access is now mostly local to the node accessing the data, and that means Varnish has to wait less, and there is less latency overhead added to its processing and can consume more of the CPU doing actual work. We will now dig into the details for how we were able to achieve these results, and we see that in Varnish we have a concept of thread pools. Our thread pool is used to partition the work that is done by Varnish in order to reduce contention when managing tasks and to accept client faster. Each pool has an acceptor thread, and all work which comes from connection in this pool is carried out by worker in this pool. By default, we populate 2 thread pools with 5 K worker each. In NUMA-aware Varnish, we pin a pool to a specific NUMA node in order to reduce the UPI traffic generated between the pools. We don't try to eliminate the UPI traffic per se, but enough that the UPI bus is no longer the bottleneck. Moving on, as mentioned earlier, one worker accepts connection per pool. The clients arrive at all available pools and are delegated to an idle worker in that pool. If no worker is available, then the accepting worker reschedules itself before taking care of more clients. In NUMA-aware Varnish, we have modified the acceptor thread to only accept clients from the same node as the NIC itself or where the data is coming from. And this is done by loading a small kernel program to apply socket filter based on the NUMA zone that the request were coming from. In Varnish, some memory are recycled in threads to avoid many memory allocation and deallocations. Such buffer are now local to the NUMA zone, and to minimize the UPI usage, the TLS buffers and workspaces are 2 important examples of this. Moving on, in order to make use of this feature, here is a bullet list of things you should be aware of. I'm not going to read through all of this, but be aware there are some requirements need to fulfill in order to use this. For instance, you need Varnish Enterprise version 6.08 R2 or newer, and you have some kernel support. You need some kernel support, and yeah, there is some things to be aware of here. Also be aware that in a non-balanced system, with, for instance, 2 CPUs, but only has 1 NIC, it's expected that Varnish with NUMA awareness will only utilize one of the CPUs, as there is no NIC to deliver traffic to the other CPU. Nash will now talk about NUMA balance system and how they can improve the situation. Back to you, Nash.
Thanks, Assad. So once we have the software optimizations in place, we need to be able to take advantage of them in hardware. And there's some things that we've done that have made taking advantage of that new software performance a little bit easier. So the latest generation of Intel Xeon scalable processors has some new features that are relevant for this use case. We have an increased memory bandwidth. We've increased the number of memory channels as well as the memory frequency. Quite importantly, we now have PCI Express Gen 4. This doubles the PCI Express bandwidth on a per lane basis. And there are also more lanes on this processor than prior generation. Additionally, the core counts have increased, the cache sizes have increased. There are new instructions that are improved performance. Particularly, some of those instructions pertain to OpenSSL. Additionally, there are some pre-developed, pre-tested configurations that are available through the Intel Select Solutions program that make it easier to get up and running with a new CDN system. They're pre-validated configurations with a recipe for how to get to some known level of performance. Additionally, we took advantage of Intel NVMEs, and particularly D7 P5510, which is a Gen 4 by 4 NVMe, as well as Intel 100 gig Ethernet adapters. So a 1-port 100 gig as well as a 2-port 2 by 100 gig card. Now, those processor features must be enabled in a system in order for the end user of that system to get any performance improvement. And so the system design that we choose to use is incredibly important for performance. If we have a poor system design, we'll get poor performance. If we have a good system design, then we can get good performance. And so in this case, this is a diagram of the system that we are using for our dual socket design. It is a NUMA balanced system. And what I mean by that is we have an equivalent amount of I/O in each type of I/O on each socket. And so what this allows us to have, with having the same amount of drives running at the same speed on socket 0 and socket 1, and the same amount of NICs running at the same speed on socket 0 to socket 1, is it allows the two processors in the system to truly be peers to one another with equivalent capability. This means that if our application gets scheduled on either socket, it can expect equivalent performance more of the time. This enables us to get better utilization of the system as a whole, as if we had, say, only 2 drives on socket 0. It is likely that we would run out of drive performance on socket 0 first and end up underutilizing that processor. With the design like this, we're able to get good utilization out of all of our I/O devices as well as all of our processors. Additionally, in the single socket case, we're interested in single socket performance. Many single socket system designs are optimized not for performance up to the limits of the processor and what can be done, but rather performance within a specific cost window. And with the system that we've used, that is not the case. This is a single socket design that is extracting all of the performance that is available. And so in our single socket server that we've used for these experiments, we have 8 NVMEs, Gen 4 by 4, running at full speed, and then 2 Gen 4 by 16 NICs that also run at full speed. And so again, just like with the dual socket case, this makes sure that we're able to get good utilization out of all of the components that are installed in the system. If we had only, say, 4 NVMEs, we may end up underutilizing the processor and the NICs and not getting all of the performance that is possible with the equipment that's been purchased. And so if we take a look at some, somebody has some background noise on the line. Thank you. If we take a look at the benchmarking results using these systems, as well as the NUMA-optimized varnish with all of its capabilities, we see some interesting things. So before getting into the exact test results, I need to cover how we tested and why we made some of the test choices that we did. And so we're using a benchmark tool called WRK. It's been around for quite some time. However, our systems, our clients that we're using to run this benchmark are limited to 100 gigabits per second each. And WRK, we've seen, has some scaling problems as we approach 100 gigabits per second. So as a result, we're using multiple clients. And to coordinate those multiple clients, we are using parallel SSH. It isn't the most sophisticated approach, but it works for our purposes. WRK, in general, will run as fast as it is able to, up to either the network limit or the processing limit of the client system. Or if you're out of performance capability on the cache node, the limit of that. But in our case, it is frequently the limits of the client. Our client is also selecting data randomly. All of our content is of equivalent popularity, which is unlike what is typically seen. Typically, there is popular content in the cache, as well as less popular content in that cache. And so the most popular segment of that typically is found in DRAM, and the less popular portions are found on disk. In our case, it is very likely that we're going to have to go to the disk for the vast majority of requests. Additionally, our clients are using their own unique data set to further minimize the likelihood of finding data in memory and force disk reads. This is nearly the worst case scenario access pattern. Our WRK parameters, such as number of connections and number of threads, are selected based on some feedback from customers, as well as some of the observations that we've seen using the tool. So for the test we're talking about today, we're using WRK with a number of threads equal to the number of physical cores in the clients, 3,000 total connections, meaning the sum of all WRK instances is 3,000 clients, or 3,000 connections rather. And we're using no inter-request delay with WRK. In general with WRK, increasing the total number of connections will require using that delay parameter to maintain the overall request rate at some reasonable level, such that the cache node can perform as expected. So let's get into some test results. So the detailed configuration here for our single socket case, we're using a 6338 Xeon Gold processor, 8 NVMEs at Gen 4x4, and 2 100 gigabit ports, in this case coming from a single 2x100 gig E810 NIC. The system is configured with 1 DIMM per channel of DDR4 3200 for a total of 256 gigs of capacity. And importantly, the system that makes this type of design possible is a Supermicro 110P WTR. Additionally, we have our content origin, which is shown in this diagram for completeness. During these benchmarks, the content is all hits in the cache node, and so no accesses are made to the content origin. Also shown are our 2 clients running WRK. This system, with its design of 8 NVMEs and 200 gig ports, is able to get very close to the line rate of those two NICs, which would be 200 gigabits per second. We're able to extract 191 gigabits per second with 100% TLS traffic for this video on demand workload with that uniform random distribution of data that I mentioned previously. Additionally, our data set is large enough that it is impossible to fit in memory regardless of our access pattern, which would force additional accesses to disk. And so if we need additional performance, we can scale this up to a dual socket system. But it has to be a dual socket system that is designed well for this type of application. And so for the system that we're using, we've kept the processor the same, only now we have a second one. We have 12 NVMEs now with 6 per socket. Again, these NVMEs run at full speed, so Gen 4x4. We now have 4 network adapters, 100 gigabits per second each. And then we are also, again, running in 1 DIMM per channel, DDR4 3200. And we're using a Supermicro 220U TNR to make this possible. Just like the last diagram, the content origin here is shown for completeness. During these tests, all of the data is found in the cache node, and no requests are made to the origin. However, because we've scaled up the capability of the system, we've also had to scale up the capability of the clients. And so we've gone from 2 clients to 4 clients. In scaling up the system from 1 socket to 2 socket, we would expect that we scale up the performance as well. And so with the NUMA awareness features in Varnish, it is now possible, with no additional changes to force NUMA locality, to get that good, almost ideal scaling. And so we've gone from 191 gigabits per second in the single socket system to 383 gigabits per second in the dual socket system. That is a 400 gigabit per second line rate. That's possible through the software optimizations that I mentioned previously, as well as a well-selected system. We have a NUMA-balanced system, we have NUMA-aware hardware, and we're able to get good performance as a result. One additional thing to note is that SNC sub-NUMA clustering is enabled on the system to improve the Linux page cache behavior. At very high throughput, the Linux page cache can become a little bit of a bottleneck, and enabling sub-NUMA clustering alleviates that problem somewhat. The workload here is the same as mentioned before. It is a video on demand workload. All of the traffic is using TLS, and it is that same uniform random distribution. However, the data set size is doubled to make sure that we're hitting a wide enough region on the NVMEs to get representative performance. For those interested, these are the full configuration details of those 2 systems, the single socket as well as the dual socket system, as well as the details of the software that was in use on those. If you'd like to learn more about these systems, Varnish, or Intel Select, there are a variety of resources available. The links here will take you to a white paper discussing this same topic with more detail. You can also visit the Varnish software page on Intel Network Builders, the Varnish software webpage for additional detail on Varnish Enterprise, its capabilities, and its full feature set. The details of the Intel Select solutions for Visual Cloud as well. And so at this time, we can get to questions.
All right. Thank you, Nash. And thank you, Paul and Assad, for your review of these solutions. Great information, lots of detail here. We do have some questions. Let me urge our audience to add some additional questions if you have them. We have these gentlemen here waiting to answer your questions. Just key them into the console, and we'll get to them as soon as possible. Let me start with our first one, and that is, and any of you all can answer this. Is the performance that we've seen here the limit of what's currently possible? And who wants to start out with that one?
I can answer that one.
All right. Thanks,
so the configurations that are shown in the testing here were selected to be high performance configurations within a reasonable cost constraint. So we selected a middle of the stack processor rather than picking the top bin processor. And we have also selected broadly available servers that are easy to locate and easy to purchase, relatively speaking. If you were to, instead of making those choices, decide to pursue performance at all costs, these same servers with this same software can be pushed farther if you are to increase the processor capability. So in this case, going from, say, the Xeon Scalable 6338 to something like the Xeon Scalable 8380 and increase the networking capability, then yes, you can push the performance higher. The software has more performance available to it, and it does continue to scale.
All right, excellent. Let's move on to our next question. Any ideas on what happens at a larger number of connections? Who wants to take that one?
Well, I can say something at least. Yeah.
Right.
So the cost, the cost of keeping connections open, so sessions, is of course non-trivial. You also have problems where you have package loss and so on. There are many non-ideal situations that might come up, and it all depends quite a lot on the severity of these things. I don't think adding half more, 50% more connection will impact this too much, but we have not tested this. At least I haven't. Maybe Nash can say something about that.
Sure. So in general, Varnish with these types of configurations can handle an increased number of connections. But as Paul mentioned, there is a performance requirement per connection. It does consume some resources to maintain that connection and to continue to feed it data over time, as well as the networking effects that become more pronounced. I don't have test data that I could present today with an increased number of connections, but I have tested with increased numbers of connections with Varnish before, and it does continue to perform as you increase that number of connections. Now, yes, it does. If you get to very high number of connections, there is a performance decrease, but I would describe it as incremental changes in performance as you increase the severity of the workload rather than a step function.
I hear you.
Would you say that covers how it behaves, Paul?
Yeah, I think it makes a lot of sense. Yeah. Of course, you also have the effect of kernel buffers, which will take some resources on the kernel. You can't allocate all of the memory just for Varnish. And so it very much depends on the nature of the connection as well as the number. And that's another reason to keep these servers close to the clients. If you can at all put a cache in New York to serve customers in New York, you should do that, because everything will just be better and easier.
A lot of variables, a lot of moving parts, but best to keep these as close to the content user as possible. Here, let's see. This one is for you, Assad. To be 100% concrete, which platforms are supported for the NUMA improvements?
So we have taken in use some technologies like eBPF and have some constraints where they are supported. So currently we say that the NUMA-aware varnish is supported using that NUMA feature at Debian Buster and CentOS 8 or Red Hat Enterprise 8 and Ubuntu Bionic, Focal, and Amazon Linux, and soon to be supported at Debian Bullseye. There is some constraints about Red Hat Enterprise 8 that has to do with SE Linux, but that is ongoing work. But at the same time, we have seen that it requires cap sysadmin, and that is not something we want to grant Varnish. So that means we have to put it into permissive mode to make use of that NUMA feature in Varnish.
All right, very interesting.
In short, yeah, you need to have a sufficiently granular support in SE Linux to make the configuration work. You need to have support for that. We can always disable SE Linux and run normally.
Interesting. All right. Let's see. Here's a question for you, Paul. I would like to run open source Varnish. Can I get performance comparable to Enterprise on a single socket system?
You can get very good performance with open source Varnish, but you can't solve the use case that we're talking about here. The persistent disk-based cache is necessary to deliver these kinds of speeds, simply because Varnish Enterprise is using the APIs necessary to do this, and support simply isn't there at the open source Varnish. You can, however, use open source Varnish to serve live traffic where you don't need a disk. But of course, I would like to point out that there are many various quality of life and things that makes running a Varnish server easier if you run Enterprise over the open source.
I getcha. Okay, here's another question. It's a little general, so tell me if you can answer this. Can we use Varnish, this solution, over the air?
I'm not sure what that means.
I wasn't either. Were we talking broadcast? Were we talking 5G?
In terms of, so if I interpret that question as mobile clients over 4G or 5G, yes, this solution could be used in that type of environment. Obviously, there will be some networking changes required since I've used all wired networking.
Yeah.
But otherwise, as long as the client can speak the HTTP and HTTPS protocols. Go ahead, Paul.
But yeah, that's exactly the point. Varnish is an HTTP cache, and this type of traffic, so everything is HTTP nowadays. Of course, if you have a satellite dish, that's not HTTP. If you have cable TV, so linear TV, that's not HTTP, but practically everything else is HTTP. I don't know about G5 broadcast, if that's something which is popular, but right now practically everything is HTTP, and that's what we are solving for. And I suspect and expect HTTP to dominate the G5 video traffic in the future.
Gotcha. Okay. That and thanks for that clarification. We did get the clarification that everybody saw that we were talking 5G broadcast for the question. And with that, we are 10 minutes till the hour, so it's time to close off the webinar. I'd like to thank all of my speakers, Nash, Paul, and Assad. A very informative webinar. I learned a lot. And I'd like to thank all of our audience members for tuning in. And if you have a whole list of resources that you can access for more information, as well as reaching out to the companies themselves. And so with that, I'm wrapping up the webinar, and thank you all very much.